When we start learning about dynamics and Newton's law, usually the first law to learn about is the so-called Newton's first law. This law is very simple to understand and to apply. Simply it says when there is no force applied on the object will maintain its original status. If the object is at rest, it will continue to be at rest. If the object is moving in a straight line with constant velocity, it will continue moving in a straight line with constant velocity. The only way to change the status of the object from rest to motion, or from motion with constant velocity to motion with acceleration or deceleration, the only way to achieve that is to act with an external force on the object. So here, if you consider this image, the book originally is at rest. At rest means there is no external force, no net external force. Okay. Now imagine pushing the book with a horizontal force greater enough to overcome the force of friction between the book and the table. Then the book will start moving with some velocity, and with time, because of the friction force, it will start slowing down and slowing down until it is stopped, because the force of friction opposes the motion. Okay. On the other hand, if you take the same situation and if you add some wax or make this surface smooth and repeat the same experiment, then the book will move faster and will be able to reach to further locations. In fact, if the surface was frictionless, no friction on it, then the object should continue moving with that velocity indefinitely. Okay. So now we understand this relationship between force and motion. In words, the first law, we say that an object that is at rest will remain at rest. An object that is moving with constant velocity in a straight line will continue doing so unless compelled to change its status by a net external force. This law is also called the law of inertia. Okay? Inertia is an expression for the tendency of objects that are at rest to remain in rest. This is the formal statement of the law. An object moves with a velocity that is constant in magnitude and direction unless a non-zero net force acts on it. When we learn about Newton's first law, usually we talk about inertia and about mass. Inertia is the tendency of an object to continue in its original state of motion. It could be at rest, or it could be with constant velocity. So the system, the object, tend to maintain that status. The other quantity that is related to inertia is the mass. Mass usually is the amount of materials in the object. It is a measure of the object resistance to changes in its motion due to a force. Okay, so we measure mass in the SI system in kilograms, and the magnitude of the mass usually is taken as a measure, as an expression of the object's resistance to changes in its motion due to a force. This is one of the applications for Newton's first law. We are all familiar with this, the seat belt in our cars. There is a mechanism inside the car. The mechanism allows us to adjust the seat belt in the way that is comfortable for us. But once something abnormal happened, we have an accident, then the sudden motion of the car will mobilize this large block underneath the seat. And this here, we have this pivot here, and you have this connection, this thread. So the motion of this large block this way will make this arm here rotate around the pivot and locks this ratchet mechanism. This way, the seat belt will be locked. It will not move. And it will act to protect us from being hurt. Okay? So this is one application of the inertia, that if we are in the motion with constant velocity, or if we are at rest, then this mechanism is not activated, but the sudden motion will activate the motion. They will activate this arm and lock here the rash to protect us. We move to Newton's second law. If you examine these images, here we have force acting on this block. As a result, the block is accelerating with an acceleration of 2 meters per second squared. Here, if you double the force, the acceleration is doubled. It's the same block, the same mass. So doubling the force will double the acceleration. It's now 4 meters per second squared. On the other hand, if you double the mass and keep the force as it was before, so the acceleration now is halved its original value. This tells something. This tells us something about the dependence on the mass. We can see that the mass plays an important role in determining the acceleration. The acceleration is directly proportional with the force and inversely proportional with the mass. Always in physics, it helps us to use formulas. So in formula form, the acceleration is equal to the net force. We have this sigma. Sigma, this is a mathematical symbol, just to tell us that this is the net force. In other words, you need to consider all force vectors, and then to find the resultant for these force vectors. The resultant, we call it the net force. So the direction of the acceleration is the same as the direction of the net force, and the magnitude of the acceleration depends on the net force and on the mass. It is directly proportional with the net force and inversely proportional with the mass. This is in Newton's second law. Very simple, but powerful and very important law. Because once we calculated the acceleration, we can go back to what we learned in chapter 3 and chapter 2 in the kinematics. Once you have the acceleration, then you can calculate the velocity. Once you have the velocity, then you can calculate the displacement, and the whole motion is understood. Okay? So when we studied kinematics, we did not ask about the cause. We just assumed some acceleration and studied the motion. Now we understand from where we have the acceleration. We have it from the net force. It depends on the net force and on the mass of the moving object. Okay? The same equation, we may write it in this form. F equals ma. F, the net force, is equal to ma. And I want you to pay attention to the vector nature of the force and the acceleration. Okay? So here force in magnitude and directions, and here the acceleration both in magnitude and direction. We have this proportionality between them, and the mass is just a proportionality constant. So when we talk about vectors, we always have in mind the 3 dimensions. Okay, so this equation between F and A means that the force along X equals MAX. The force along Y, net force along Y, means mass by acceleration along Y, and net force along Z is equal to mass by acceleration along Z. The unit for force is in Newton. In the SI system, the unit of force is in Newton. And 1 Newton is equal to 1 kilogram meter second squared. From this equation, the force is measured in newtons. 1 Newton is equal to 1 kilogram, the unit for mass, multiplied by meter per second squared, the unit for acceleration. 1 Newton of force is equivalent to 0.225 pounds. Both Newton and pound are units of force. The mass in the metric system, the SI system, is measured in kilogram, and in the British system is measured in slug. Slug, the acceleration in this case would be in foot per second squared, and 1 pound is equal to 1 slug foot per second squared, just like 1 Newton is equal to 1 kilogram meter per second squared. Usually in physics, science at large, we use SI units most of the time. This is just to complete the picture so that you know how to relate the US customary units or the British system to the SI units. Understanding. An object can move even when no force acts on it. True or false? An object can move even when no force acts on it. What do you think?
True.
Thank you, Emerson. Yes, it is true. So if the resultant of the force is 0, either because no forces are present or the vector sum of the forces adds to 0, the object can still move, but the motion will be with constant velocity, not an accelerated motion. Okay? Motion with constant velocity. For example, if you are on a jet liner in the sky, it's cruising with constant velocity, say 500 miles per hour. Constant velocity. There are forces there, but the forces add up to 0, and because of that, it is cruising with constant velocity. If you are driving your car on the highway and you put the cruise control, say 70 miles per hour, constant velocity means the net forces now are 0. There are forces, otherwise the car will not move. But these forces adds up to 0, so that now you are able to cruise and you are able to move with constant velocity. Okay? So yes, an object can move even when no forces acts on it. If a single force acts on an object, this is a different situation. If a single force acts on an object, the object accelerates. True or false?
True.
Any suggestion? Roxanne, any suggestion? If a single force acts on an object, the object accelerates. This is true. Yes, thank you. Okay? Because a single force is a resultant force. Okay? The resultant force cannot be zero. The resultant force is what matters to us. If the resultant force cannot be zero, then there will be acceleration. The acceleration is not zero. Okay? So to have a single force is different from having a group of forces that may be add to zero resultant. If the net force acting on an object is in the positive x direction, the object moves only in the positive x direction. True or false? Tricky, huh? The answer is false. If the net force is in the positive x direction, the acceleration will be in the positive x direction. However, the velocity of the object does not have to be in the same direction. Okay? So the acceleration has to be in the direction of the force, but the velocity is not necessarily along the same direction as that of the acceleration. For example, the projectile motion, which we studied in chapter 3. Okay, for a projectile motion, the acceleration is always downward, g, 9.8 meters per second squared. But the velocity may be up, maybe horizontal, maybe down. Okay? So this statement is not correct.